Hi, my name is Tim Liebrecht, and I'm here with Dr. Christopher Papil, the founder of BraneCell. Dr. Papil, tell us a little bit about your founding team and tell us a little bit about BraneCell.
Sure. Thank you very much, Tim. Glad that you could interview today. First of all, we're a very experienced team. So we're doing this from a point of view of science, love of physics, love of engineering. And like, for example, Dr. Sams is very well known in the industry, in the material science. And that love of this science has kept us going for quite a bit of time. And as I mentioned, we have our first priority as patents in 2012. So we're very early on and before many others. This is about a quantum neural network made out of a 2D molecular array. And there is precedence for this in natural quantum processes, which we will go into in another video. It's too long to talk about here. We see this as business progressing in two stages, because there's just the holding of information that's encrypted, and then there's processing information, which is much harder to do. So just the holding of information that's encrypted, that's what we call QID, in kind of an analogy to RFID, but this would be quantum ID, and that we'll be able to encrypt it with a quantum encryption, and we'll be able to match it together with our QSDC, which is the quantum secure direct communication. So from end to end, there can be never any tampering or counterfeiting. Strongly correlated nodes, they can also emit light. So we had a Department of Defense grant that was about what we call QSDC, which is quantum secure direct communication. And the quantum secure direct communication means that no one can tamper with it. It's an absolute communication that only the sender and receiver can get the message. So but the ultimate goal is quantum machine learning, which is done on AI chips. We make the hardware for that based on this molecular array that I talked about. So this is not a semiconductor-based system, so we're able to do a new kind of manufacturing. That new kind of manufacturing, it looks a lot like 3D printing. It's called atomically precise manufacturing. So it's almost like you take a scanning microscope and just almost putting the atoms where you want them. At this point, it's not as fast as one would like it to be, but with more research and development, we can get it to a practical position where it would be 1/100th of the cost for overall CapEx to do a fabrication facility. We wouldn't need a $10 billion facility anymore to do that. It would be less than $100 million. So it's distributed manufacturing of AI chips. Distributed is always good. It kind of democratizes what we're doing. It doesn't just an elite group of people can do it who have that massive amounts of money. It could be done anywhere, including in West Virginia. So I think that's an important motivation. Quantum machine learning has the opportunity to have high information density, and that's what we're shooting for, both because some quantum processes can process things much quicker. They can be done in a classical way, and also our chips themselves are 150 times smaller than semiconductor analogs to them. So what we talked about in the video was a very high revenue to R&D, revenue potential to R&D costs, financial ratio works in our favor with what we're doing, because the R&D is not as high as, for example, in pharmaceutical industry, but the value of the product per kilogram in the overall market is better from our point of view, for our product. So we're talking about low-cost CapEx. There are many potential buyers, so early investors have an opportunity if they come in now. We already have some angel investment, and we had some government Department of Defense grant money, but any other investors that come in at this point, there would be a great opportunity for exits, because there's so many companies out there. This is a very hot topic, quantum AI, or AI itself. And so NVIDIA or Alphabet or AWS, there's many buyers out there. So I think that is quite assured when we get success to the minimum viable product. So this is fitting perfectly to national and international trends for manufacturing onshoring and AI hardware, both very important topic matters these days. Especially in the United States, it's one of the goals, but in many countries they want to do more onshoring of their own manufacturing. For critical supply chains, it's a safety issue. So granted patents we have before many of the important players, like before Xanadu, before Alibaba, before many of the names that you hear. We have patents go back to 2012, and they're granted. We have granted claims. And but we are definitely seeking new investment right now. That's one of the impetuses for this current video, to as an explainer to people so that investors can take the next step with us after they get an introduction through this video. So ultimately, the emergence of what we're seeing here, which from the scientific, like one of the interesting points of this whole thing, what we haven't talked about yet in the video, but I just mentioned it at this time, is sort of from the science point of view, not from the business point of view, but it's about the emergence of form. So when you have highly correlated many-body systems where you have 2 to the n possibilities that are all of equal energy, it creates what they call the emergence of form. But when we talk about AI, there's a correlation in the information realm. So there's 2 kinds of realities. In the physical realm we're very familiar with, but at the nanoscale it starts to get closer and closer to the information realm. In the information realm, we think of it in terms of mathematics, but it's actually a realm in itself where the 2 have to talk when we're talking about AI. So the quantum neural network shows structures and forms which is used in the AI realm, in the machine learning realm, for something called, like ReLU polytopes. So polytopes are like, different kind of polygons or whatever in mathematical space, and these are holding information that the AI uses to analyze something and categorize it, and for us to understand and give all the interesting things like large language models and things that we know about from AI. And when you look at the structures, there may be one on your screen now, we show what it looks like in the physical realm for surfaces that have nodes, and then how that correlates in the information realm. And it's absolutely fascinating that the 2 have to work together in AI, and that's what we're bringing forward in our work.